Good morning students. Let's see the continuity of D block element. We done already ionization energy and some important bits regarding that, and we go for density here. Okay. So density of D block elements, especially we are discussing a 3D transition series. So what is density? Simply density D is equals, you know very well, mass by volume. Mass by volume. This is density. Density. And what about this one? Mass. And what about this one? Volume. Mass and volume. Okay. And so here volume you can also measure size also. Size of the atom. Okay. So what is the relation between density and mass? Density is directly proportional to mass. That means if density is increases, mass is also increases. Or mass is decreases, density also decreases. Directly proportional relation. Okay. Density is directly proportional to mass. And what about volume and density relation? Density is inversely proportional to volume. That means if density is increases, volume is decreases. Or if density is decreases, volume is increases. Inversely proportional relation. Okay. So let us come to 3D transition series. 3D transition series. What about these 3D transition series? That is from scandium to zinc, and copper and also zinc. Copper and also zinc. Okay. And let's see now. And here copper and zinc, we will need to discuss about these two. That's very important. Okay. So generally density of copper is higher than density of zinc. That means density of copper is greater than density of zinc. Then what about the size here? Size, or we should also consider here volume. So copper has more density, That means what about the size of copper? Density and size relation, density and volume inversely proportional, am I right? That means size of copper is smaller than size of zinc. Okay. Copper is less than zinc. That means zinc has more volume than copper. Okay, clear? So zinc has more volume. That's why its density more volume, less density. So zinc has less density. Okay. So let's see. Zinc, cadmium and mercury. These are belongs to 12th group in the periodic table. Am I right? Okay. So what about these two? Okay. So these are very soft metals. With less density. Okay. And mercury, very well about this one, it has less density. Compare these two also, and it is in liquid state at room temperature. Very well it is liquid metal also. Liquid metal. Clear? And what about this one? D block metals has more density than S block elements. S block elements. Okay, keep it in our mind. And osmium and indium has highest density in the periodic table. That means they occupy more volume. Okay. Why size of zinc is more than copper? We already discussed in the previous class. Okay. Generally from left to right in the periodic table. Size of atoms decreases, but there is exception. Copper has less size than zinc. There is exception condition that due to screening effect. We discussed in the previous class about this one. Okay. Actually, according to this left to right, the size of the atoms are decreases. That means copper is bigger than zinc. But what we conclude here, due to the screening effect, size of zinc is more than copper. Originally, when we are moving from left to right, sizes of the atom decreases. When comparing with copper and zinc may be smaller in size, but it has occupy more volume. That means it has more volume, more space. That means its size is more than copper. Why? That is effect of screening effect. That inner electrons between the nucleus and outermost shell act as screens. Then attraction between the nucleus and outermost electrons of zinc is very less, and there is completely fulfilled d electrons in zinc amarite 3d10 it has. Okay, that electrons are present in between the nucleus and outermost electrons of the zinc. So more electrons are available in the inner orbits, so repulsion takes place. Okay, so that means attraction forces are very less, so size increases in the case of zinc. So what is the main reason? Due to the screen effect. Okay, keep that in our mind. So this is the size and density relation. Copper has more density. Why? Because it has smaller size than zinc. Okay, this is the relation. Keep it in our mind. And some of the important physical properties of D block elements, that is malleability. Okay, some of the important physical properties of D block elements: malleability, sonorous and ductility, lustrous. lustrous nature. These are the important physical properties of D block elements. Let's see. What about malleability? Malleability. Okay. So malleability, for example, gold. Rm we call it is gold. What is the Latin name of gold here? Rm. Okay. So it has malleability property. Malleability means a metal can be drawn as thin sheets. Thin sheets. A metal can able to drawn as sheet like. That property is called as malleability. So metal can able to make as thin sheets. Okay. That property as called as malleability. What about sonorous? Sonorous means make the sound like bell. When we hit with hammer, a bell metal gives some sound, So the metal which can produce sound when we hit with some others, that property is called as sonorous. Bell like sound it produces. Okay. And ductility means a metal can be drawn as wires. Okay. So for example, gold ring. Okay. So we can mold the gold as ring-like structure. If any metal can be molded as a ring-like structure, that property of metal is called as ductility. So gold has ductility property. Okay. So lustrous means shiny nature. For example, gold has shiny or not shiny. The shiny property of gold or any metal is called as lustrous nature. So keep it here. So when lustrous metal exposure to air or moist, that means in presence of vapor, okay, they can lose their lustrous nature. Okay, because lustrous metal has loosely held electrons. Okay, that means in the lustrous material they has electrons, they are very loosely held to the nucleus. Okay, not strongly attracted with nucleus. Okay, so loosely held electrons are present. When they exposed to air, they lose their lustrous or shiny nature. Keep it in our mind. Okay, this is the important one here. In the next property, radius of D block elements, especially here we are discussing 3D transition series. Radius or atomic size. Radius or atomic size. Okay. So let us take 3D transition series. So scandium, titanium, vanadium, okay, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay, clear? So what is the electronic configuration of scandium here? So simply argon 4s1 4s2, 3d1, 3d1. You have to observe this configuration, 3d1. And here it is 3d2. What about here? 3d3. What is the atomic number here? 21, 22, 23. Okay. And what about here? 24, 25, 26, 27, 28, 29, 30. These are the atomic number, and this one is called the electronic configuration. 3d3. What about here? 3d5. Chromium has special electronic configuration. Don't forget that. That is argon 4s1, 3d5. Okay. Manganese also here 3d5. Iron 3d6, and here it is 3d7, 3d8. Okay. And copper 3d10, and also this one 3d10. What about copper? It has also special electronic configuration 4s1, 3d10. You know very well. Okay. Here we are discussing about radius of these 3d transition series. 3d transition series. So here this is 4s2, this is 4s2. Okay. This is 4s1, and this is 4s2, 4s2 and 4s2, 4s2. Okay, this is 4s1 and this is 4s2. So almost in s orbital there is 2 electrons, exception in copper and chromium, but where the variation is there from one atom to another atom. So 21 to 22, when electrons are increases from 21 to 22, where the electron is enter here it is 3d1. Am I right? Clear? When its atomic number is increases up to 22, then it will become titanium. That new electron enter into 3d only, 3d1, 3d2. And in the case of vanadium, so one more electron enter into 3d3. So the electrons enter into 3d orbital. Am I right? So let's see. This is the nucleus. Clear? Nucleus means what is the charge present at the nucleus? Plus. Plus means protons. What type of particles are present in the nucleus? Neutrons and protons. You know very well. And protons carries positive charge. And what about neutrons? It is chargeless, 0. Okay. So, and these are the orbits. You know, orbits. Okay. So now this is ns. Electrons are present. Orbitals are present. Here n-1 d orbital is present. So last cell is called as valency cell here. Valency cell. Electrons first enter into ns, then after, okay, they enter into n-1 d. Okay, this is the last one before cell, this one. Okay, suppose here we are discussing about 3d. That means what is the value of n here? It is n value is 4 here. The value of n is 4 here. Then 4 as, what about this one? 4 minus 1 d, that means is equals to 3d orbital. Am I right? 3d. Clear? So first electrons enter into 4s, then after that electrons enter into 3d. So here electrons mostly enter into 3d. Am I right? So this is valency cell and this is the nucleus. Am I right? This is inner orbit. What we call it is inner orbit. That means the orbit between nucleus and outermost cell. What about this one? Nucleus, center of the atom. So now this is inner orbit. That means in between the nucleus and outermost cell there is a orbit that is called 3d. Clear? The electrons which are present in 3d, okay, is called as inner electrons. Inner electrons. This is inner orbits. Keep it in our mind. So scandium 3d1, then titanium 22. It is 3d2. That means the electron enter into 3d only. And here also 3d. So the newly coming electrons after moving left to right, scandium 3d1, where it is entered in 3d, last electron. What about titanium? 3d2. So one electron is increased. That electron is also entered into this 3d orbital is only. So mostly all the electrons are entered into this orbit. While we are increasing, it is increasing from left to right. What happened? The electrons in 3d increases gradually. Am I right? Clear? So ns electrons is there is no change. It mostly consists 2, exception in the case of chromium and copper. Mostly it consists 2, except in chromium and copper, where it consists only 1 electron in s. Am I right? So it is proton. Okay. So keep it in our mind. So now let's see the graphical representation here. Note here, generally from left to right in the periodic table, that means in the period of periodic table, atomic size or radius decreases. Okay, decreases. Okay, keep it in your mind. Now let's see, this is the radius. Take the graph between radius and atomic number. Atomic number we denote with Z, you know very well. So atomic number is increases 21, 22, 23. That means electrons are increases one by one. Okay, and consider their atomic radius. So what is the representation here? These are the values, atomic radius value, increasing order, 0 to high, and here it is atomic number is increases 21 to suppose 30. So here it is scandium, starting with scandium and titanium, vanadium, chromium, this is manganese. Okay. So these are the values, compare these values. Scandium to manganese, what happened? Atomic radius is gradually, slowly decreases, am I right? Atomic radius is high for scandium. So, it decreases very slowly, okay? So, scandium to, keep it in our mind, scandium to manganese, atomic radius slowly decrease, not very much, okay, it is slowly decreases. So when come to iron, these three are, one is iron, another one is cobalt, another one is nickel. So it is middle of the curve, you know, middle of the curve is almost all same. That means radius, atomic radius of iron is almost similar to radius of cobalt, is almost similar to radius of nickel. Constant simply. Their radius is constant, almost constant in the graph. Am I right? There is no change. They process similar atomic radius here. So when it comes to next two elements, this is copper and this one is zinc. Radius is increases means size is increases, keep that in your mind. So when comparing with copper, these two are very, very important. This point is very, very important. Okay. Copper and zinc. So actually we are expecting moving from left to right, sizes are decreases. That means atomic radius is decreases. Okay, slowly decreases. But at middle of the curve, these three are having similar. I will explain why it is happened. Similar size, similar atomic radius. So after moving to copper and zinc, we are expecting zinc has very small size than copper. Why? Because left to right decreases. That is the phenomena. Why it is happened, I will explain. But here zinc size is more than copper. Okay, keep it in our mind. So let's see. So what is the electronic configuration of copper? That is clearly argon 4s1 3d 10. Am I right? 3d 10. So what about zinc? Zinc, that is argon 4s2 3d 10. 3d 10. Let's see. This is the nucleus. nucleus has positive charge. This is suppose this is 4s, this is 4s and this is 3d10. Nucleus has positive center 3d10. So this is 4s electron, am I right? 1 means electron is there. So 3d10 electrons, am I right? This is the nucleus. What about this one? Valency cell. So electron has negatively charged particle or not? Negatively charged. What about nucleus? Nucleus has positive center. So what about this between these two? So there is some interactions is there. Attraction forces are there. So this nucleus positive charge interact with this negative charge. Okay. If it is very strongly attract this outermost electron, so this positive charge very strongly attract the outermost electron, then size is decreases. Size is the decreases. So which orbital here? 3d orbital. So 10 electrons are available. Electron has which charge? Here we have 10 electrons. Electrons process negative charge, am I right? So this is electron and this is electrons, am I right? So repulsion takes place. More repulsion takes place between electron and electron. More repulsion takes place. Okay. So more repulsion takes place. These inner orbit electrons, that means 3d10, and between the outermost electrons repulsion takes place. Repulsion takes place. So repulsion takes place means what happened here? Attraction between nucleus and ns electrons are very less. So size is increases. Size is increases. Okay. And one more point we have to discuss here. This is one of the reason. Size is increases. And what about here? Same phenomena here also. This is zinc. This is 4s2 electrons and 3d10. So more repulsion takes place between these two. 3d10. More repulsions. Even than copper also. More repulsions means big size. Big size than copper. Clear? So the repulsions are very more in copper. That means it has more size than zinc. Okay. So that's why the atomic radius of zinc is more than copper. So compare these values. Zinc is here, copper is here. This is the, draw the line. This value is at this higher radius when comparing with copper. Okay. Let's see. In 3D transition series, from scandium to manganese, their atomic radius slowly decrease. Okay. And from iron, cobalt and nickel have almost similar atomic radius. Copper and zinc has more atomic radius than copper. That means zinc has more volume. That means bigger in size. Okay. So here to discuss about these three factors, we need two things here. One is screening effect. In the view of repulsions, I am already explained. Another way we can explain these three, that is, one is screening effect. Okay. Another one is effective nuclear charge. Screening effect simply, and effective nuclear charge. Okay. So keep it in our mind. Screening effect is directly proportional to atomic radius or size, and inversely proportional to effective nuclear charge. That means screening effect is more, atomic radius is more. If effective nuclear charge is less. What is effective nuclear charge here? You just simply remember. Okay. This is positively charged nucleus, am I right? Nucleus of atom, where protons are present. They have positive charge. And this is valency cell. Valency cell. Suppose here electrons are present, outermost electrons we call it is. So the electrons which are present is in between nucleus and outermost electrons are called as inner electrons. Inner electrons. Okay. Clear? So effective nuclear charge means how these positive charge affect the valency cell electrons. How much attraction it has, these positive nucleus center, how much attraction with outermost electrons. If it is very strongly attract the outermost electrons, very strongly attract, that means effective nuclear charge is very high. That means effective nuclear charge high means these positive center very strongly attract the outermost electrons. Then what happens? Its size is decreases. Size is decrease. Attraction more, size is decrease. That means effective nuclear charge is high. Okay. So if here effective nuclear charge is very less, then size is high, and screening effect is also high. Clear? Effective nuclear charge means that positive center with how much effect it can attract the valence electron. If it is strongly attracts means it has highly effective nuclear charge. Then automatically size is decrease. Okay, and this is the phenomena. If effective nuclear charge means, that means strong attraction with outermost electron, size is decreases. If it is weak effective nuclear charge, that what happen? It is weak attraction, then size is increase. Okay, keep it in our mind. So screening effect means, screen means the electrons which are present these inner orbits. That means the orbit which are present nucleus and outermost electrons called as inner orbits, and these are electrons are called as inner electrons. These electrons act as screens. Screens or shield, just like a wall between nucleus and outermost electrons. So if more electrons, more inner orbit electrons are present, they act as a good screen. They prevent the attraction between nucleus and that electrons. So attractions are very weak when good screening effect is there. That means more inner orbits are present. Okay. So attraction less means effective nuclear charge is less. Clear? So these electrons are easily attract the electron when the screening effect is weak. Okay. So not much electrons are present. Okay. So it is easily attract the outermost electron, but it is act as good screen. What happened? attraction is very less, then atomic size is increases. Okay. These inner electrons are act as a good screen. Then attraction between valency and nucleus is very less. So size is very decrease, very small. If these are very poor shielding effect, that means not act as a good screen, then attraction is very high. Then what happens? Size is decrease. Okay. That is the screening effect. Okay. So this is the relation between screening effect, atomic radius and effective nuclear charge. Okay. So strong effective nuclear charge, that means it has weak, inversely proportional, weak shielding effect. So strong attraction means size is decreases. Okay. Keep that in your mind. So that phenomena takes place here. Okay. From here what happened in this case, effective nuclear charge, okay, less than screening effect. Okay. That means we have to mention like that. Screening effect has greater than effective nuclear charge. That means less attraction takes place. Less attraction takes place between the electrons. Okay. So good screening effect you have to mention. Good screen. Okay. So less attraction. Okay. Effective nuclear charge is very less. Okay. That means what happened? Less interaction. That means size is increases. So zinc has more size than copper. Okay. So what about here in the case of these two? And effective nuclear charge almost similar to screening effect. Both are having in similar quantity, but there is no change in their radius. Okay. And in this case, gradually decreases. Gradually decreases means effective nuclear charge is higher than screening effect. Okay. So strong attractions are there. So atomic radius is gradually decreases, not very much high. Okay. So outermost electrons are better to attraction with nucleus. So size is decreases. That means not very much increase in atomic radius. It decreases very slowly. Okay. Keep that in our mind. Good shielding effect means it maintains more distance between nucleus and outermost electrons. Simply you remember atomic radius of copper is less than zinc. Okay. Radius of copper is less than zinc. Density of copper is more than zinc. Larger size. What about zinc here? Larger size. Smaller. So simply we can represent that graph here. Radius and their atomic number. This is zinc and copper. Iron, nickel, cobalt, almost all constant. Keep it in our mind. And scandium, titanium, vanadium, chromium and manganese slowly decreases. Radius is radius is slowly decrease. Here it is constant. Again here radius is increase. Radius increase means size is increases. Okay, clear mark to this one. So this is 3D transition series. Which series? 3D. So similarly we have 4D and also 4D and also 5D. Okay, same, slowly decrease and increase. Okay, but in between these two series, radius of 4D is almost similar to radius of 5D. I am already explained that. Okay, but in the 5D series, initially slowly decreases and constant and again increase. Again 4D also slowly decrease and again increase, constant and increase. In between these two groups, what happened? Radius of 4D is almost similar to radius of 5D. Okay students, again we will meet on tomorrow. New concept, that is heat of atomization. And after that, very important topic, that is explanation about chromium and potassium permanganate.